Bonjour. Hello, everybody.
Hello.
Thank you. Hello, Blake. Let's see. There's a new homework that's due on Wednesday. That's midterm 3 is next week, last day of next week. About the quiz, it talked about stability of a pendulum. And this was because I wanted to introduce you to something non-trivial. Typically, we have a pendulum. Let's say this is a hinge about which a pendulum is hanging. And let's say the pendulum is rigid in the sense this rod is rigid. You can also have a string onto which you attach a mass M. But another possibility is that you have a real physical rod. And we all know that if we let it go, it will actually oscillate around the vertical axis in such a way that if you include friction also, it will eventually slow down and come to rest at that point. But what is non-trivial here is that one might not realize that what would happen if you were to keep, since it is rigid, it can actually stand here. So let me displace it slightly from the vertical. And it is expected that this will fall off. If you displace it slightly and it will fall off. This comes to the category of what is called Kabit's pendulum. And the idea is that if you were to oscillate this, so this can be done even with a hand, if you were to hold on to a pendulum and vertically oscillate this. So now there are two possibilities. You can oscillate this point vertically or horizontal. So this is a horizontal oscillation, and this is a vertical oscillation. And it turns out that if you were to just have simple horizontal oscillation, you cannot balance this pendulum, even though we sometimes play around by having a vertical rod in our hand and we try to balance them. That's with feedback. We are looking at the pendulum and we are making it stabilized. But that's not what we are talking about. Here, if you kill this horizontal and have just the vertical oscillation, and if you were to oscillate it about 23 hertz, it depends on the length of the pendulum also. So let's say about 20 centimeter long pendulum, if that was the case, and if you were to oscillate it about 20 to 25 hertz faster than 25 hertz, then this will balance. You can actually move it, displace it a little bit, and still it will be stable. And that has a lot of applications. First of all, it's non-trivial, so it should be of interest for you guys. And anytime you're trying to come up with something interesting, these are the non-trivial ideas you can use in different contexts to come up with new designs if you want. So I wanted to introduce that to you. It's also called inverted pendulum. Without, there are a lot of inverted pendulums there with feedback. That means to say you look at the top of it and then make a sensor and change it. But that's not what we are talking about. This is stable, intrinsically stable. You can say dynamically stable. You move it in such a way that it is actually stable. So that was about inverted pendulum. We want to now talk about a new concept, which is, again, probably you're familiar with using it, and sometimes it's also used colloquially. And this will be called momentum or linear momentum. Later on, we will talk about angular momentum. So just to distinguish that, let's call this linear momentum. And by linear, we mean something momentum when things are going in a straight line, or we're not talking about circular motion. I think that's again, what's the theme here? We have Newton's law, and we have realized that, or we have learned that Newton's law is very useful for describing motion or even predicting what will happen to a particle in a small amount of time in the future. It can do a good lot of things, and that's a mathematical equation. Sometimes when you have a mathematical equation, you can manipulate that equation and come up with new ways of expressing the same concept. And that's what we did in introducing energy. We pretty much multiplied the Newton's law with a displacement, and we learned that energy concept can also be used to solve some problems. And here we want to similarly introduce the idea of momentum. So let's go back to Newton's law. Newton's law tells us that if you have a system, which is typically the mass m that you're analyzing, or the motion you're describing. So the motion is, when we say loosely, when we say motion, we mean the acceleration of the mass m. So the acceleration of the mass m is given in terms of, or the product of mass times the acceleration is equal to the vector sum of the forces acting on the mass m. So we have seen that we have first identify these forces and then add them vectorially, divide it out by mass, and we get the acceleration. Once we have acceleration, integrate that, we can get velocity. Once you have velocity, if we integrate it, we get the position as a function of time. So that's pretty much everything is there in that equation, but sometimes it's nice to see the same concept in different ways. So this time what we do is, or earlier we multiplied this whole equation by a displacement, right? We took a dot products with respect to displacement. This time we will multiply this whole thing with time. So let's say we have a small differential time. So remember, position, displacement, and change in time are two quantities we began the whole description of motion. Here then we have mass times acceleration is change in velocity over change in time. When I'm multiplying by the differential in time, I'm getting another dt, which will basically cancel out, right? So this becomes a total change in velocity. That's what we are getting. And all the forces get multiplied by time. This is a scalar. Time difference does not have any vectorial nature in it. So vector times a scalar is well defined. So each component gets multiplied by that time difference. So what we have is F1 evaluated during that small displacement in time, plus F2, the vector force F2 multiplied by the small displacement in time, and so on. That's your expression, or Newton's law, when you multiply by dt. As I said, you can cancel out this dt. And if you allow me, I'll just erase this, even though for you guys it might be more difficult to erase things because you're writing on a notebook. But if you allow me, that saves me some space here. So that's dt canceled out. And now let's integrate each of this term. Whatever I do on one term, I have to do on every term. So I integrate each of this term. Very similar to what we did when introducing energy. There we integrated with respect to position. Here we are integrating in time. So dt has to be integrated some from initial time to final time. So t1 to t2, let's say, T initial to T final. T initial to T final. Okay. That's T initial to T final. And same thing here, T initial to T final. When we were doing the integration in the context of energy, we realized that, oh, this could depend on the path, right? We are working in a three-dimensional space, and to go from one point to the other, there are lots of paths possible. But here T is unlike displacement. If you have T is first of all monotonic. T only increases, right? T, time is a special function. You don't go back and forth in time. It has to be monotonic. Once you cross a point, you cannot come back. Like you cannot come back from the future to the present. So it's monotonic, and you have to reach from one point to the other, and it's linear, like in the sense that it is going along a line. So there's only one way to go from T initial to T final. So there is no path dependence to begin with. By construction of the parameter time, there is no path dependence in that. So there is no need to talk about path. So this is unique. So this integral is well defined and always unique. Having seen that, we notice that the left-hand side immediately becomes very simple, because this is an integral we know. Whatever be the system, whatever be the velocity, as far as the mass does not depend on the velocity, this integral is straightforward. This is dx, like integral of dv is simply v integrated from initial to final. So that's final minus initial that to begin with. So that's immediately done. So let me write that down. So mv final minus mv initial. So whatever this quantity is, it depends only on the final and initial points in time. And on the right hand side, we have integral of this forces. And we will define that to be a physical expression. Let's just copy it down again. So since we have these quantities explicitly showing up, let's define a few things. Let's define momentum P as a P final and P initial. At any instant of time, the product of mass and velocity will be defined to be the momentum of the system or of the mass m. So this is momentum. If there is one particle, you say that's the momentum of that particular particle. If there is a sum of them, this could be a system. Remember, it could be consisting of 3 or 4 masses, and then it's the momentum of the total system. What is the units of momentum? Immediately, we when it came to energy, it was such a common thing that it was we gave it a new unit. We said joules because it is so common. Here we don't give it because it is just 2 variables and it is easy to write. We simply say it is kg meters per second. So you don't usually associate a new unit with momentum. That is, so on the left hand side we have P final minus P initial then. And what is force times distance? So let's define force, or let me put the left hand side to be the new quantity. So let's define integral of a force with respect to dt. It could be any force, let's say F1, right? And this is T initial to T final. This will be defined to be, at this point, we will just call it J. This will be what we'll call impulse. And this will be useful in studying situations where we do not know the details of what the force is as a function of time, but we know the total expression because it depends only on the initial and final points. And in those kind of situations, it will be useful to talk about impulse. And we will see that a collision process, like a car coming and hitting another car, those situations, this concept comes out handy. In that, or using those terminology of momentum and impulse, we can define P final minus P initial, which is nothing but change in momentum, right? So these are vectors. So this is change in momentum is equal to the sum of all the impulses, which is a vector quantity, sum of all the impulses. So then this statement that change in linear momentum is equal to the vector sum of impulses is the statement of Newton's law written in the language of momentum. That's okay, algebraically, all this is good. Mathematically, it seems just one step. I mean, technically speaking, we just multiplied by t, right? And then there were some definitions and we wrote that equation. Let's do some examples and clarify what this concept means. Question?
So
Yes, please.
the final and initial momentum are vectors in this
Yes,
case?
they are vectors because momentum is velocity, right? It's proportional to velocity.
Okay, so then how come final and initial velocity aren't vectors then?
Tell that again.
How come final and initial velocity aren't vectors then?
That's, you mean here?
Yeah.
Because that's a mistake. I should have copied it here and it should have written final, right? Velocity is a vector, so I forgot to write that, or it's a mistake.
Okay, thank you.
Okay, thanks for asking the question. Yeah, that clarifies. So, and always, if you have a vector on the right hand side, it has to be a vector on the left hand side. That's my bad. Thank you. Yeah. Okay. Any other questions? Okay. Okay. Let's do a simple example where this shows up. And broadly, we want to talk about what is called a collision. So what do I mean by collision? Collision, 1S or 2S? Collision. Is that correct spelling? Anyone?
Yeah, it's 2 L's.
2 L's, right? Yeah, thank you. Okay. Okay, so a collision, let's think of a very simple scenario here. So let's say we have a table. So that's a table that represents a table, and that's a ground. Right? So this is ground, and that's a table. And we have been talking about situations where you have a person, let's say this could be a human, jumping off a table. We typically talk about a ball that is rolling off a table, but in this case, let's say we have a 1 meter high table, and there is a kid or a student jumping off the table, and we know how far you will go, right? So this was a problem we discussed. But what we did not discuss is what happens right when it touches the ground. We know very well now at this point how to describe, given an initial velocity, what would be the velocity right before it touches the ground. But now we want to talk about a collision process. By that we mean what happens during the time the person touches the ground and comes to a rest. So right before the student reaches the ground, he or she has an initial velocity, let's call it V initial, pointing vertically down, and it comes to a rest pretty quickly, right? This whole process here, the collision happens in a fraction of a second, typically in a millisecond or maybe 10 or 20 milliseconds. So it's very, very small. And these days with very expensive cameras, you can actually capture this moments very nicely. And there are nice YouTube videos on that, especially when a water droplet is falling along. It comes sometimes as very elegant videos there. So we want to talk about that scenario, right when it is in the process of deformation and touching. And that's a complicated system. And the forces that are acting on this are typically changing with time in a not in a very controllable manner. But nevertheless, we want to discuss this. So let's say during that collision process, we have, that's your simple model. We have the mass m. This is the mass of the person who is jumping, and we are not interested in the jump part that we have understood reasonably well. And now we want to talk about right when it is coming into contact. That's a collision part, right? So this is what I mean by collision. And we will use the word collision in a very broad sense. When two cars are coming and colliding, that also we will call collision. When two masses are coming in touch with each other, that's also we will call collision. If I were to push on this blackboard and get pushed away, that also will be a collision. So it will be discussed in a very broad sense. During the collision, what are the forces acting on it? Let's assume that everything is going vertically down. That is mg acting downwards, mass times gravity. And that's pretty much a constant force. Gravitational force or acceleration due to gravity is 9.8, and that doesn't change with time. But the normal force is what everything is happening in the normal force. To begin with, the normal force is 0. Right before it touches the ground, normal force is 0, because unless you are in touch with the ground, normal force doesn't even start acting. So the moment you start touching on it, there is a small normal force, and as you push on it, so as you're falling onto the ground, the normal force keeps increasing, and eventually you come to a rest, and again normal force becomes a constant if you want. So if you were to plot, so as a function of time, if you were to plot, so this is time and this is normal force, let's say magnitude of the normal force as a function of time. If I were to plot this, it starts from 0, and it has some complicated structure. We don't know what exactly it is, and it comes to a constant value very quickly. Like this is when it is at rest. So it becomes once. So this after this point, this is at rest, and here again it has not touched. Right, begins to touch ground. So at this point in time, it starts to touch the ground, and after a while, it comes to rest. There is no more deformation. It has come to equilibrium. And during that period of time, normal force goes somewhere from 0 to a constant value in a complicated manner. And if I were to talk about the impulse, remember what is the impulse? J, due to the normal force, is the integral of the normal force as a function of time. An integral is a sum, of course. You add up all the normal forces at each instant of time, each infinitesimal instance in time. But if I were to integrate them, that's basically the area underneath this curve. So this is that area. If I were to add up all this area, the area will be, there is a y-axis, there is a force, which is newtons, and on the x-axis, you have time. So the units will be in Newton seconds. So this area represents impulse. And it is measured in impulse in Newton second. And what will that be equal to? This area as a whole is equal to the final minus initial time. That's the interesting point. Whatever it seems like, oh, that's a curve we don't know, we won't be able to talk much about it because we don't know the structure of the normal force. It depends on how the student is jumping, the process of how much you bend your legs, that decides your normal force. And so we might not be able to know much, but no, because this total area is basically momentum, final momentum minus initial momentum. So let's see what we can talk about. So this is equal to, let's come back and for this process, we would say this is final momentum minus initial momentum. That's equal to the impulse. So impulse due to the gravitational force plus the impulse due to the normal force. But let's say whatever the details are, there is an impulse which so this is a broad description. We say that, let's say this is some effective force times delta t. For how long has this mass been in touch with the ground? So because we don't know the details, we will just be satisfied with the average of that, and we will show that still we can learn a lot about this process. We will be able to understand a few things about why we do when we are jumping, why do we fold our or why do we bend our legs. Right? So let's calculate this effective. So this is F effective, or the effective force acting on the person, and we want to be pretty much talking about how does this time matter. So let's say this is final velocity minus initial velocity divided by delta t. Very much like saying force is change in velocity over time multiplied by mass. Since mass times velocity is momentum, that's the same thing. But here it is slightly more, because we are using the idea that integration actually, when you integrate it from one point to the other point, it only depends on the initial and final point. So we're using the fundamental theorem of calculus here, if you want. Okay, so the final momentum is 0 because it's going to come to rest, so we don't worry about that. Minus of the initial momentum. Initial momentum is mass times velocity, so that's mass, times velocity initial, it is going down, so that's minus j. So that's the unit vector. I'm saying j is in the upward direction, so that's j hat, velocity is going down, so let's say that's your v initial. So putting all the vectors coming out, and that's delta t. That's all variables, but I'll make this simple. And this is minus j hat times mass times v initial over delta t. That's all it depends on, how much force you experience right when you collide with the ground, right? When you jump off from the table and you reach the ground. When you were very young, probably you didn't learn the skill that how you're supposed to bend your legs, but very quickly we all naturally, based on instinct, we learn that bending the legs helps a lot, or probably we have it ingrained in our genes itself. So let's see how it matters. So let's say m is equal to 50, or let's say 45, 50 kg, let's say 50 kg with two digits. V initial, of course, V initial, I don't really have to provide the V initial. I can give you the height of the table, and that pretty much decides my V initial, be using conservation of energy, right? That is, usually you don't lose much of energy in friction there. So that's almost decided there. But let me say that V initial is known. Whatever is the height it contributes to, a velocity of, let's say, 6 meters per second. That's just to simplify the problem. Otherwise, I have to use the height to calculate the V initial, which we studied last week. So let's, for simplification, let's use this is 6 meters per second. And the time, now time has two ways I can process that. And that is, if this was a skillful person jumping, they would bend their legs very well, and that means you are in touch with the ground for a longer duration. So there are two possibilities. One we will say is a very skillful, doesn't take too much jump, and one would think it is trivial, but imagine a situation that you're not actually folding or bending your legs. If you do not bend, it takes smaller amount of time, and that's about this will have a lot of error. I'm just simply saying it's about 10 milliseconds. It's in the right ballpark, but that doesn't mean that it is really correct. It surely depends on who is jumping, how you're jumping, but it's in that ballpark. So that's your time. And if you were to bend, actually, you take a lot more time. So let's say this is about 100 milliseconds. So it's about 10 times larger. So this is no bending of your legs. And this is when you bend. Hopefully that's readable there. And that is when you bend. So let's calculate what the two forces are. So this is no bending. So that's force that you experience on your legs will be, since it's in the denominator, it will be significantly larger. Oh, I made a mistake, right? I said this was two negative signs. This should be positive. Right? So the force will be acting up when you jump down. You're pushing on the ground is actually pushing you upward. So the force will be in the upward direction. These two negative signs add up to give you a positive sign. So the weight is, so this is plus J times 50 times 6.0 divided by 10 milliseconds. So it's 10 into 10 raised to minus 3 seconds. And that's meters per second, and there's another second that's an acceleration on kg. So that gives you the units in newtons, and this is equal to 5 into 6 is 30. So that's 3 zeros on top, and 3 zeros comes from the bottom. So that's a million already there, and that's 10 raised to 5. So that's J hat 3.0 into 10 raised to 5 newtons. That seems like a large force, but it's always compared to, we have to compare it with something else. So let's see what is the force if you do bend your legs. And again, let's calculate. This time we get 50 times 6.0 divided by, this time it's 100 into 10 raised to minus 3. Numbers are the same except that you divide it by 10. So this also comes out to be large, but this is 10 times smaller than your earlier expression. So if your legs are designed actually to be able to tolerate this much of force, you give an extra 10 times larger, 10 times usually comes out to be significantly larger. You have a chance of breaking your legs and so on. But the idea I wanted to show here is that during a very small fraction of a second, when we are talking about a collision kind of a process, even then it is, if there are quantities that depends only on the initial and final points. Like it doesn't matter what actually happens during the collision. Lots of things happen, a lot of complicated things that we cannot control. But there are quantities where the initial and final has a lot of information about what happened. And that's where momentum comes in. And we will actually talk about very specific systems where we can really precisely talk about the momentum very well. So let's do another example. Any questions on this before I proceed?
Just checking that no result where you do bend the legs is times 10 to the fourth.
Yes, 10 raised to 4, because there is a, this is a 10, that's 100, right? So it just reduced by, maybe the white was not showing up. Is that better?
Yeah, thank you.
Yeah, okay. So the idea here is not really the actual size of the number. Relatively, it is 10 times larger. So just by bending your legs, you have actually reduced the amount of force that's acting on you. And that force, of course, is distributed in time. Like effectively, that's the force acting on it. So at some point, it is very small. Sometimes it is very large. It's an average force we are talking about. And again, now it seems like, oh, this is an average quantity. Can we really do something concrete out of this? And yes, we can. And that's the examples we'll talk about now. So most of the collision problems that happens, if the momentum is conserved, then we can talk a lot. We have a lot of predictive power in that. Okay, so let's do those an example in that context. So let's do another example. So this time, this is talking about, think of a skating ring, and you have two people. One is a kid and one is an adult. Right? So this is a kid and an adult. Think of a kid with their parent, right? And that's in a skating ring. And I'm keeping it as a skating ring so that friction is not effective there. But again, if the time is small enough, that's not very relevant. But let's say this is frictionless. So this is a skating ring. So we can keep this frictionless. And now we say that we push onto each other. So there are two friends or a kid with their adult parent. They push onto each other. So there is you keep your hands together and you can push onto each other, and they will get thrown off from each other, or thrown off or pushed away from each other. And we can ask which one, who will actually get more velocity with them. So that could be the question we are analyzing. And let's go back, and we want to analyze it in terms of momentum. So let's represent these two masses with just simple blocks representing them. So that's your M1 and that's your M2. And the collision process is, we are not interested in afterwards what happens. Of course, if you push it, there is an initial velocity and they go away. They push away or they move away from each other. We know that how to describe that part of the motion. But here, with what velocity do they move? That's what we are interested in. So let's say this is M1 and M2. M1 is smaller than M2, and that this cross, by this cross, I mean there is a collision happening. That means to say you push onto each other and push away from each other. Right. So what are the forces acting on M1? So on M1, there is M1G acting, and there is a normal force acting. I should be drawing this on M1 itself, but just for clarity, I have brought it away from it. So that's M1 and that's M1G. And M2, similarly, that's M2G and N2, the normal force N2. What are the other forces acting? There is one more force acting. You're pushing onto each other, right? So there is a force due to contact, since you're pushing with respect to each other. So this is a force onto by one. This is a force on to by one. And there is an action and reaction pair on M1. That's exactly the same force acts, but in the opposite direction. Right? This is C1, 2. Right? This is on 2 by 1. If M1 exerts a force on M2, M2 has to exert an equal and opposite reaction force on M1, and that's Newton's third law, right? That's your 6 forces acting on the total system. If I were to treat M1 and M2 as a single mass, then I'm not interested in C1 and C2. These will cancel each other, right? They are opposite to acting in the opposite direction, equal magnitude, so they don't even come into picture. But if I'm interested in actually the motion where they split with each other, then these play an important role, as we will see. What about the normal force? Nothing is happening in the vertical direction as far as motion goes. So N2 will balance M2G all the time, and N1 will balance M1G all the time. In fact, all the vertical forces are irrelevant in this problem. Everything is happening in the horizontal direction, and that's what is more important. So let me write my equation as, remember your momentum, momentum in the final direction, final point, that means after the collision. By after the collision, I mean after you have pushed and separated from each other, right? That is 2 points in the collision initially before you started pushing, and an instant after you separated from each other. So that's a final point minus P initial. And momentum here is associated with 2 masses. That's equal to the impulse due to all these forces. There are 6 forces here. Let me write this as M1G, impulse due to JM1G, plus impulse due to normal force N1, plus impulse due to M2G, plus the impulse due to N2. Let me write this in parentheses so that they come in pairs, right? And eventually there is an impulse due to 1, 2 plus impulse due to 2, 1. I have to squeeze that in there, but it's 1, 2 and 2, 1. Notice M1G is always equal to N1. So at each instant, those 2 forces cancel out. So the impulse will cancel out. So this will be equal to 0. So impulse due to the normal force plus the impulse due to the gravity will equal 0, because these forces inside itself equate to 0 all the time. So if you integrate them, so all the zeros, when you add up, you will again get a 0. Integration is nothing but adding up all, or integration is nothing but addition, right? So that's equal to 0. Same thing with N2 and M2G. So that's also equal to 0. And these 2 forces also, these 2 are contact forces. Notice it's a very complicated process. It depends on who is pushing onto the other. How I push on this blackboard will be very different from another kid coming and pushing onto this blackboard. So these details of these forces are very different, but it doesn't matter. These 2 are always equal and opposite in direction. So this also goes to 0. That's the important result, that whatever causes collision, typically there are 2 masses. Whatever forces they are exerting, they are internal forces, and they are always equal and opposite to each other because of Newton's third law. And the impulse due to that will always come out to be 0. And if the internal forces go away, then usually we have P final minus equal to P initial. That need not always happen. Only in certain kinds of collisions it happens. Notice that it was necessary that the vertical forces had to balance each other. So if this collision was happening in the vertical direction, like there is a mass falling from the top and colliding with another mass in the vertical direction, in that case, the normal force need not balance M1G all the time. That was an example we did earlier where a kid was jumping off from the table. In that case, we cannot use conservation of momentum, or this final momentum is equal to initial momentum. This happens only when all the external forces has to cancel, first of all, And secondly, the internal forces has to balance. So two things happened here. One is external forces were equal to 0. Total external force was equal to 0. And second was that internal forces balanced or internal forces cancelled. If these two situations happen, then we have the simple result that the final momentum is equal to the initial momentum. And if we have that, if we have such a situation, notice how we proceed. What is your final momentum? There are two masses, M1, V1 final. Everything is happening horizontally. So let me say it is plus or minus is what happens. So notice if I were to, so that's your, if I were to draw it here, right? So this is M1 moving away with V1 final. And that's M2 moving away with V2 final. There are two velocities in there going in opposite direction. Initially, they were both 0. So that's M1, V1 final. It's going to the left, so I put in a negative sign in there. But there's another possibility that let me say I don't know V1 final. Let me get the answer to be whatever it comes out. If it comes out negative, I'll interpret that it's going to the left. Plus M2, V2 final. That's my final momentum of the two blocks. Has to equal to M1, V1 initial plus M2, V2 initial. If both are at rest, the way we talked about our situation here, both were at rest, so that's equal to 0. Both is equal to rest, so that's rest, right? So that's equal to 0. Then these two have to be the same. So we can say that V1 final has to be equal to minus of M2 over M1 times V2 final. So a couple of conclusions we can make from here, even without having any numbers in hand, that the velocity of the kid, which we said was mass 1, has to be in the opposite direction of the velocity of the adult, which is again intuitively clear. If you push on with each other, you go in opposite direction. But if you're in a skating arena where you're not used to having no friction, or imagine you're in space where there is no friction, it will be hard for you to imagine what will happen if you were to push onto something. Or in space, what happens is that if you were to throw something you're holding on to, so let's say you're having a water bottle in hand, and if you were to throw that out in space, just because you have to conserve momentum, you will be thrown back, right? That's your velocity. In this case, you will be having a larger velocity. But if you're having a very heavy object, you push onto something, you get thrown away with, now the question is it with a larger velocity or with a smaller velocity? Notice M2 over M1 in our problem, that's the adult's mass over the kid's mass. We can say that this is larger. If that's larger, the velocity V1 will be larger than V2. So magnitude wise, V1 final, magnitude wise is greater than V2 final. And of course, directionally, they are going in opposite direction. We will do more examples on this, how two cars coming and colliding. We can talk about them in the next class, and we'll classify collisions as elastic and inelastic collision there. I'll stop here now. Thank you.
Have a good night.
You too. Like. Questions? If not, let me close the video.